Welcome to Lecture 26 on the interaction representation. Last time we developed an expansion for the time evolution operator u of t and t0 in powers of h of t, and we explained that this was not the best way of formulating the expansion if we wanted to think of a system that had a time-independent Hamiltonian that was subjected to a time-dependent perturbation, and we wanted then to look at an expansion of the evolution of the system in terms of the perturbation. So let's review exactly what we had done last time. Last time we showed that the time evolution operator u of t t0 took the wave function from time t0 and evolved it to time t. We got an explicit expression for this time evolution operator. We expressed it as a time-ordered product or a time-ordered exponential, where with a t symbol in front to indicate the time ordering, and then an exponential of minus I over h bar integral from t0 to t dt prime h of t prime. And we caution that you have to really be careful and not think that to evaluate this operator, I take my Hamiltonian, I integrate it, I multiply by minus I over h bar and take the exponential of it. That is not what the time-ordered exponential is. What the time-ordered exponential is what's given in the line below. It's this expansion, just like you would expand a power series for the exponential. So there's a minus I over h bar raised to the nth power. There's a 1 over n factorial. And then I have this n-fold iterated integral, integrating my time index from t1 to tn. All the integrals go from t0 to t. And what I have inside as the integrand is the time-ordered product of the Hamiltonian operators for each of the different times. And recall, the time-ordered product says latest times to the left or earliest times to the right. And so for whatever integrand point, t1, t2, all the way up to tn that I have, I order my factors h of t according to which time is the earliest. We can instead re-express that integral as a single integral, and because there are n factorial different orderings of those n objects, the single integral will involve a nested integral that goes where the upper limit of the previous integral is the integration variable of the next integral. So what I mean by that, let's look at the innermost integral. It'll go from t0 to t to the n minus 1. The next integral would go from t0 to t to the n minus 2, all the way up to the integral. The second integral goes from t0 to t1, and the final integral goes from t0 to t. If you look carefully at that, tn is always the earliest time, and tn minus 1 is the next earliest time, and tn minus 2 is the next earliest time, and so forth. So that's what a time-ordered product means. And if we took the derivative of this, especially if we look at that last expression, you can see that t only appears in the integrand of the last integral. So if we take a time derivative of this expression with respect to t, multiply it by I h bar, you see what we're going to pull out is an integrand that involves evaluating the integrand at time t. Well, the only thing that depends on t1 is an h of t1 and the integrand limit on the second integral. So the h of t1 will become h of t, the integrand limit will become t, and we'll find that because the derivative of this object looks exactly like the object with one lower power, so the derivative of the nth order term will look like the n minus 1 order term. If I factor out a minus I over h bar, I get exactly the same summation that I had before. And so indeed what we're going to get is if we multiply that whole thing by I h bar, we'll get just the h of t out in front, and then we'll get the time evolution operator, u of t t0, appearing on the right-hand side. And indeed, that is the equation of motion that we said the time evolution operator must satisfy. Now, by taking the explicit derivative, we can show you that the equation actually is satisfied by this expression that we wrote down, which is the exact solution for this time evolution operator. Okay, let's go through that carefully in case that was too fast. So when we take the time derivative, as you can see, it's only the top index of that first integral is where t appears. And so when I take that derivative, I'm going to pull out a factor of minus I over h bar. I'm going to have an IH bar because I'm multiplying that by the derivative. And I'm going to get a term that has one fewer number of Hamiltonian operators in it. So it's going to only go up to Tn minus 1. In fact, as I look at this, it went just a little bit too fast in going from the top line to the second line. There were two things that took place there. We shifted the index so that the sum is going from n equals 0 to infinity there. But as I had said before, what happens when I take that derivative, I'm going to remove the t1 integral. I'm going to be left with this t2 through tn integral. The t1 term, that's the limit of the t2 integral, becomes t. The h of t gets pulled out because that's the latest time. It's all the way on the left. And I'm left with a product of h of t2 all the way out to h of tn. And of course, the n equals 0 term has nothing because the derivative of 1 just will give me 0. And the first term, when we take the derivative, we're actually pulling out this factor h of t, and what's left is just the number 1. And you see, if I just take my old n index and replace it by n minus 1, then I'm going to get the full u of t0. If this is not clear to you, I strongly recommend you pause the video, work out by hand how you take that derivative, and really make sure that you understand that this equation of motion holds. Okay? All right, so as we had mentioned before, for many problems that we're going to find of interest, the Hamiltonian is going to have a special form. It's going to have an h0, which is time independent, and then it's going to have a v of t, which is the time dependent perturbation. We tend to think of the v of t as being small, but in reality, if the v of t can actually be a particularly large operator, as long as it interacts with the system where it's non-zero for a short period of time. So you can imagine applying some kind of a pulse to the system, which might even be a large amplitude pulse, but if it's applied for a short enough time, it still will effectively be just a perturbation of the system. So we would like to figure out a perturbation theory expansion, which will be an expansion in V, not in H. And before we jump into that, we're going to have to look at some of the different pictures for thinking about time evolution in quantum mechanics. So we start off with the Schrodinger representation. This is something that we should all be familiar with. That's the case where we have all of the time dependence on the wave function, and we have the time-dependent Schrodinger equation, which says the h acting on psi of t is equal to I h bar d by dt of psi of t. For the moment, we can assume that the Hamiltonian is independent of time. And now let's think about what does an expectation value of an operator look like in this Schrodinger representation. Well, we'll call that expectation value a of t. That's just a function of time. And I have to have a bra psi of t, I have to have the a operator, and I have to have a ket psi of t. For the moment, we're going to assume the operator a also has no time dependence. Nevertheless, because the wave function has time dependence, this expectation value will have a time dependence. Let's take the derivative of this expectation value, the derivative of a of t. We can call this the equation of motion for the expectation value of a. So it's going to have three terms in it. It's going to have one term that involves the derivative of the bra. It'll have one term that involves the derivative of the operator, and it'll have one term that involves the derivative of the ket. Now, of course, the derivative of the operator is 0 because we explicitly said the a operator has no time dependence. So that leaves us with just two terms in the expression, and we can take each of those terms and re-express them in terms of the time-dependent Schrodinger equation. So the time derivative of the ket psi of t will equal minus I over h bar multiplied by h acting on psi of t, and the time derivative of the bra is the Hermitian conjugate of that, so that's I over h bar psi of t with h acting to the left onto psi of t. So now when we collect these two terms, we find we get an overall factor of minus I over h bar psi of t with the expectation value of the commutator of a with h. And so we can put this all together and we find I h bar d by dt a of t is equal to the expectation value of the commutator of a with h in the state psi of t. Now all of the time dependence is coming from the wave functions in the Schrodinger representation when the derivative of the Hamiltonian with respect to time is equal to 0. Okay, there's a competing representation for this, which is called the Heisenberg representation. What we do in the Heisenberg representation is we remove all the time dependence from the wave function. You can think of this as saying, let's look at evaluating that expectation value with respect to psi of t0. Well, how do I get there? Well, I take the Schrodinger wave function psi of t and I write that as u of t psi Heisenberg. You can think of psi Heisenberg as psi of t0. You can think of u of t as really the time evolution from t0 to t. And indeed, if I do this, then that wave function has no time dependence. All the time dependence is now in the operator u of t. To remind you, when the Hamiltonian is time independent, that time evolution for u of t is e to the minus I over h bar h times h operator times t. So now we defined a Heisenberg of t as u dagger of t, a operator, u of t. That's a product of three different operators. Then a of t, the expectation value, will be psi Schrodinger of t, a psi Schrodinger of t, which we can rewrite as psi Heisenberg, u dagger of t, a, u of t, psi Heisenberg. And then using this new notation that we've used, that would be the expectation value of psi Heisenberg, a Heisenberg of t, psi Heisenberg. All of the time dependence now is in the operator because the wave function is time independent. Let's work out the equation of motion for this object. Of course, we expect it to be the same as the equation of motion for the other object, the Schrodinger expectation value, because since we started out with the initial expression being in terms of the Schrodinger wave function, that a of t, it's actually the exact same thing. So let's go ahead and calculate its derivative. The time derivative of the Heisenberg matrix element of a with respect to time is going to be I h bar d by dt of u dagger multiplied by times a times u plus u dagger a I h bar d by dt of u. Now we have to remember the equation of motion for u. I h bar d by dt of u is equal to hu. And that means I h bar d by dt of u dagger is equal to minus u dagger h. Because we have to take the Hermitian conjugate of the original equation of motion. When we put that all together, you see it's going to be a u dagger commutator of a with h multiplied by u. And now we can actually move the u dagger u inside the product. What we're essentially doing is we're inserting a factor of 1, which we're going to rewrite as u dagger u, between a and h, or between h and a in each of the terms in the commutator. And when we do that, you see we're going to get ah of t, and then the other term will be u dagger hu. But of course, u is just e to the minus I ht, and h commutes with e to the minus I ht. So that u dagger commutes with the h. I can move it to the other side and use the fact that u dagger u is equal to 1. And as a result of that, the h does not become h Heisenberg of t. It's just still the same old Schrodinger picture Hamiltonian. And so we get I h bar d by dt, ah of t, is equal to the commutator of ah of t with the Hamiltonian h. And in this picture, all of the time dependence is in the operators. If you like, we can think of this as the same way that you would do classical mechanics with Poisson brackets. It's very popular in quantum mechanics textbooks to describe things that way, but of course we know most of us never really worked with classical mechanics in terms of Poisson brackets, so it's not necessarily something that's particularly useful for us in this day and age. All right, well, we're talking about time dependence, so we'd better figure out how to do this in the case where the Hamiltonian actually depends on time. What we're going to do is we're going to proceed very similarly now. Here we're going to have to introduce 2 times into the time evolution operator because that's required in order to make this work. Still, the Schrodinger wave function psi s of t can be expressed as u of t t0 psi Heisenberg of t0. And then ah of t will be defined as u dagger of t t0, a Schrodinger of t, u of t t0. Now you might ask, why in the world does that operator in the Schrodinger picture have a time dependence? Well, it could be that the operator has some intrinsic time dependence. Suppose I took an operator that was cosine omega t times the operator x. Then it has an intrinsic time dependence, and that would be the Schrodinger operator, and we're now trying to calculate what the Heisenberg operator is. We also find that now the Heisenberg Hamiltonian will develop time dependence, and the Heisenberg Hamiltonian in this picture will be u dagger of t t0, h Schrodinger of t, u of t t0. I do want to caution you that this Heisenberg Hamiltonian does not satisfy the same time-dependent Schrodinger equation with a wave function as the Schrodinger Hamiltonian does. That's something you can think about, but you can easily derive this yourself by doing the same substitution for the Schrodinger wave function and taking the derivatives. And you'll see that indeed the object that is involved in the time evolution in the Heisenberg picture from the Schrodinger equation of the wave function, it would be slightly different from this. Nevertheless, we're still going to call this the Heisenberg representation of the Hamiltonian because that is in complete analogy with the way we're describing the general operator AH of t. All right, so let's go ahead and calculate the derivatives of this. The equation of motion in the Schrodinger picture of the time evolution operator is still the same even when the Hamiltonian depends on time. So I get IH bar d by dt u of t0 is equal to h Schrodinger of t u of t0. And so when I take the time derivative of AH of t, IH bar d by dt AH of t, I'm going to now get three terms. I have IH bar d by dt of u dagger times h Schrodinger of t times u, plus IH bar u dagger time derivative of a Schrodinger of t, u of tt0, plus IH bar u dagger of tt0, a Schrodinger of t derivative with respect to time, u of tt0. Okay, we do the same substitution, equation of motion for u and for u dagger. For u dagger, I get a minus u dagger of tt0, h Schrodinger of t. For u of tt0, I get plus h Schrodinger of t, u of tt0. And of course, the derivative with respect to time of a Schrodinger of t, well, that just sits there. There's nothing I can do about that. Now, of course, u dagger, h Schrodinger, a Schrodinger u, I insert this u dagger u, which is equal to 1, inside. There's a typo there. There's a u dagger that should not be there. It's the first u dagger should not be there. That expression should read u dagger, a Schrodinger. And what we're going to do there is we're going to recognize that u dagger h Schrodinger u is h Heisenberg of t, and then u dagger a Schrodinger u is a Heisenberg of t. And so what we find is IH bar d by dt a Heisenberg of t is equal to the commutator a Heisenberg of t with h Heisenberg of t plus IH bar d a Heisenberg dt of t with a partial derivative. That last term, what that means is I'm doing the time derivative of the Schrodinger operator with respect to time and putting that into the Heisenberg representation. I unfortunately don't have a really good way of writing that down, and so it looks like it's exactly the same as the left-hand side, but it isn't. It really is what is written below. It means IH bar u dagger of tt0 d a Schrodinger of t dt u of tt0. That's what that last term is. Maybe I should put a tilde on it or move the h to the left of the argument of t. There's no great way of figuring out exactly how to do that. Nevertheless, in these notes, I didn't write it very well, so please be sure you do not get confused by that point. That derivative there, it's the Heisenberg representation of the time derivative of a Schrodinger of t. Okay, this seems like a good place for us to take a break from this lecture. I will present the second half of the lecture, which will start with interaction representation in just a moment. I encourage you again to pause the video, pull out a piece of paper, try to go through these derivations by hand, make sure you really understand exactly how all of them go.